The famous version of this story begins in 1950. Physicist Enrico Fermi was working at Los Alamos National Laboratory. During lunch, he and several colleagues were talking about space travel, reports of flying saucers, and whether intelligent civilizations might be common in the galaxy. At some point, Fermi reportedly asked, "Where is everybody?" That sentence became famous because Fermi was not simply asking why aliens had not landed on the White House lawn. He was thinking about time. The Milky Way is ancient. Its oldest stars formed billions of years before our sun. The galaxy is roughly 100,000 light-years across and contains more than 100 billion stars. Those numbers are difficult to feel, so let us shrink the problem. Human beings have had radio technology for only a little more than a century. We have sent spacecraft beyond the outer planets for only a few decades. On a cosmic calendar, our technological life has lasted less than the blink of an eye. Now picture a civilization that appeared just 1 million years before us. 1 million years sounds enormous from a human point of view. It is longer than our species has existed in its current form. But compared with the age of the Milky Way, it is almost nothing. That civilization would not need magical faster-than-light engines. It would not need to violate physics. Even slow spacecraft could gradually move from one star system to the next. A ship reaches a nearby star. A settlement grows. Centuries later, that settlement sends ships to 2 more stars. Those settlements eventually do the same. The expansion would not look like one heroic vessel flying across the whole galaxy. It would look more like a chain reaction, slow from the point of view of a person, but quick compared with cosmic history. Even if each step took hundreds or thousands of years, a civilization could spread through a large part of the Milky Way in far less time than the galaxy has existed. That does not mean every civilization would choose to expand. It does mean that if technological life has appeared many times, and if even one society chose to spread, the result might eventually become difficult to miss. There could be probes in old star systems. Industrial activity could alter planetary atmospheres. Large energy projects might produce unusual heat. Artificial signals could cross interstellar space. Civilizations might build habitats, move asteroids, or leave machines operating long after their creators were gone. We do not need to imagine a galaxy packed with aliens. One long-lived civilization could be enough to change the appearance of the galaxy. And yet, when we study the sky, the Milky Way still looks natural. Stars behave like stars. Planets behave like planets. Dust clouds glow where physics says they should. Strange objects exist. But so far, none has survived careful investigation as confirmed alien technology. This is the first important point. The Fermi paradox is not based on the claim that scientists know alien life must exist. We do not know that. It is based on a tension between 3 ideas. First, the galaxy is extremely large. Second, the galaxy is extremely old. Third, technology can leave detectable evidence. Put those ideas together, and the absence of obvious evidence becomes a question worth asking. But there is also a trap here. When people hear the word paradox, they sometimes assume science has discovered a contradiction. It has not. We do not have enough information for that. The Fermi paradox is better understood as a warning that at least one of our assumptions may be wrong. Maybe life is not common. Maybe intelligence almost never evolves. Maybe civilizations do not survive long enough to become visible. Maybe interstellar expansion is much harder than it looks on paper. Maybe advanced societies have no interest in broadcasting. Or maybe we have barely begun to search and are mistaking our ignorance for silence. Every explanation solves one part of the mystery but creates another. If life is rare, why did it begin on Earth relatively early? If intelligence is common, why do we see no technology? If civilizations hide, what are they afraid of? If they die, what kills them? And if we simply have not searched enough, how large does the search need to become before silence starts to mean something? That is why Fermi's question has lasted. It is not one mystery. It is a doorway into nearly every mystery connected to life, intelligence, technology, and survival. Rehuk. The galaxy had billions of years before us. And once astronomers began discovering planets around other stars, the question became much harder to dismiss. For most of human history, planets beyond our solar system were only an idea. Astronomers assumed they probably existed, but proving it was difficult. Planets are small, dark, and overwhelmed by the light of their stars. Seeing one beside a distant sun is like trying to spot a firefly next to a lighthouse from thousands of miles away. The first confirmed planets found around a sun-like star were announced in the 1990s. Many early discoveries were enormous gas giants orbiting incredibly close to their stars. Worlds so unlike our own solar system that they forced astronomers to rewrite basic ideas about how planetary systems form. Then came more sensitive instruments. The Kepler Space Telescope watched the brightness of more than 100,000 stars, searching for tiny dips caused when planets crossed in front of them. TESS continued the work across nearly the entire sky, focusing on planets around nearby stars. By 2026, NASA's confirmed exoplanet count had passed 6,000, with thousands of additional candidates still waiting for confirmation. That number does not mean 6,000 possible Earths. Many known exoplanets are hot gas giants, frozen worlds, scorched rocky planets. Our detection methods also have strong biases. Large planets close to their stars are easier to find than small Earth-like planets in wide orbits. But the discoveries changed one assumption almost completely. Planets are not rare exceptions. They are a normal part of star formation. Some stars have one planet. Others have tightly packed systems with several. We have found planets around stars similar to the Sun, around cool red dwarfs, around dead stellar remnants, and even around two stars at once. The galaxy is not a collection of lonely suns. It is a galaxy of worlds. In 1961, astronomer Frank Drake organized a meeting at the Green Bank Observatory to discuss the search for extraterrestrial intelligence. He needed a way to structure the conversation, so he wrote an equation. The equation does not predict how many alien civilizations exist with any certainty. It breaks the problem into smaller questions. How often do stars form? What fraction of stars have planets? How many planets could support life? How often does life begin? How often does life become intelligent? How often does intelligence create detectable technology? And how long does that detectable phase last? Multiply those factors together, and you get an estimate of the number of civilizations in the Milky Way that might be detectable right now. Some parts of the equation are now better understood than they were in 1961. We know planets are common. We know that small, rocky planets exist. We know that water, carbon, and organic molecules are not unique to Earth. But the later parts of the equation remain almost completely unknown. We do not know the probability that life begins on a suitable planet. We do not know whether complex life is a likely result or a cosmic accident. We do not know whether intelligence tends to evolve, whether technology tends to follow intelligence, or how long a technological civilization usually survives. We have exactly one confirmed example for every one of those questions: Earth. That is not enough to build reliable statistics. It is like trying to understand every ocean on every planet by studying one cup of water. Still, the Drake equation is useful because it shows where the uncertainty lives. Suppose there are 100 billion stars in the Milky Way. Suppose only 1 in 10 has a planet with conditions that could remain suitable for life. That would still leave billions of potentially interesting worlds. But potentially suitable does not mean inhabited. A house can have electricity, water, and empty rooms without anyone living inside it. A planet can be rocky, temperate, and chemically rich without life ever beginning. This distinction matters because popular discussions often jump directly from planet in the habitable zone to second Earth. The habitable zone only describes the distance where liquid water might exist on a planet's surface under the right atmospheric conditions. It does not guarantee oceans. It does not guarantee a stable climate. It does not guarantee oxygen, and it certainly does not guarantee forests, animals, cities, or radio towers. Venus sits near the inner edge of our sun's habitable region, yet its surface is hot enough to melt lead. Mars lies near the outer region, but today it is cold, dry, and exposed to radiation. Habitability is not a label a planet earns once and keeps forever. It is a relationship between a star, a planet, an atmosphere, a magnetic field, geological activity, chemistry, time, and chance. Earth itself has not always been friendly to complex life. For much of its history, there were no animals, no plants on land, and almost no oxygen in the atmosphere. The planet went through asteroid impacts, massive volcanic events, global glaciations, and multiple mass extinctions. Life survived, but survival was never guaranteed. So the discovery of thousands of exoplanets did not solve the mystery, it sharpened it. We now know that the raw material for planetary systems is everywhere. What we do not know is how often a planet crosses the long distance from chemistry to biology, from biology to intelligence, and from intelligence to a civilization capable of making itself known. Planets are common, life may not be, and before we assume the galaxy should be filled with voices, we need to ask the most basic question of all. How difficult is it for life to begin? Every living thing on Earth shares a connection to the deep past. The trees outside your window, bacteria in the soil, whales in the ocean, insects, mushrooms, and every human being alive today all use related biological machinery. Our cells store information in DNA. They build proteins using similar molecular instructions. They rely on many of the same basic chemical processes. That commonality strongly suggests that all known life descends from an ancient shared population. But somewhere before that shared ancestry, something extraordinary happened. Non-living chemistry became biology. Molecules began copying information. Boundaries formed. Chemical reactions became organized. Systems appeared that could maintain themselves, reproduce, and evolve. Scientists study possible pathways for this transition under the field known as abiogenesis. There are promising ideas. Some research focuses on shallow pools, where wet and dry cycles could have concentrated organic molecules. Some looks at hydrothermal vents on the ocean floor, where heat and mineral gradients may have supplied energy. Other work examines how RNA-like molecules might have stored information and helped chemical reactions occur before DNA and proteins took over their modern roles. But no laboratory has recreated the full path from simple chemistry to a self-sustaining organism exactly as it happened on early Earth. We know life appeared. We do not yet know how likely that appearance was. This uncertainty creates two completely different possibilities. In the first possibility, life begins easily whenever conditions are suitable. Give a rocky planet liquid water, useful chemistry, and enough time, and sooner or later something starts reproducing. If that is true, microbial life may be widespread. It could exist beneath the ice of ocean moons, under the surface of Mars, in warm layers of distant atmospheres, or on worlds we have not yet discovered. The universe could be alive in a quiet, microscopic way. In the second possibility, the origin of life requires an extremely unlikely sequence of events. Perhaps the right molecules must appear in the right place, in the right order. Perhaps most planets produce organic chemistry, but never cross the threshold into evolution. If that is true, Earth may represent a rare accident. The fact that life appeared relatively early in Earth's history is often used as evidence that life begins easily. Earth formed about 4.5 billion years ago. Evidence suggests life was present by at least 3.5 billion years ago, and possibly earlier, although the oldest claims are difficult to confirm. That sounds fast. But there is a selection effect hidden inside the argument. We are here to observe a planet where life began early enough for intelligence to evolve before the sun made Earth uninhabitable. If life usually takes 8 billion years to begin, observers like us would not appear around a star that remains stable for only a limited time. We could only find ourselves on one of the lucky planets where the process started early. So our own existence makes early life on Earth interesting, but not conclusive. This is a recurring problem in the Fermi paradox. We are trying to estimate what is normal while standing on the one world where every necessary step happened successfully. We do not see the failed planets. We see the winner. Consider how many separate transitions were required. A stable planet had to form in a useful orbit. Liquid water had to persist. Complex chemistry had to develop. Life had to begin. Life had to survive impacts, climate changes, and geological upheaval. Cells had to discover new ways to capture energy. Photosynthetic organisms eventually transformed the atmosphere. Complex cells appeared. Multicellular organisms evolved. Nervous systems developed. Animals moved onto land. Large brains became useful. A species developed language, cumulative culture, tools, agriculture, industry, science, and electronics. We often tell this story as though each chapter naturally led to the next. But evolution has no destination. It does not aim for intelligence. It responds to immediate pressures. A bacterium that survives and reproduces is not a failed attempt at becoming human. It is a successful organism. For roughly 3 billion years, life on Earth remained microscopic. That is most of our planet's biological history. Complex animals arrived very late. Technological civilization arrived in the final fraction of the final fraction. If Earth's entire history were compressed into one day, human civilization would appear only in the last instant before midnight. This means a planet can be alive for billions of years and never produce anything that builds a radio telescope. When we search for extraterrestrial intelligence, we are not merely asking whether life exists. We are asking whether life repeatedly follows one very specific path, and Earth gives us reasons to doubt that it does. Eyes evolved independently in different lineages. Flight evolved more than once. Social behavior appeared in many species. These repeated solutions suggest that evolution sometimes rediscovers useful strategies. But technological intelligence, at least in the form capable of communicating across space, appears only once in Earth's record. That may mean it is extremely rare, or it may mean it changes the planet so quickly that nothing else gets the chance. We do not know. The only honest answer is that the transition from chemistry to civilization contains several doors, and we do not know how hard any of them are to open. Perhaps the first door is almost impossible. Perhaps the final door is. Or perhaps the real barrier appears only after a civilization becomes powerful enough to affect its own future. That possibility has a name: the Great Filter. Rehook. What if the hardest step is still ahead of us? The Great Filter is one of the most disturbing ideas connected to the Fermi paradox. It begins with a simple observation. If the galaxy contains many suitable planets, but we see no widespread technological civilization, then somewhere between a lifeless planet and a galaxy-spanning society, something must be very difficult. That difficult step, or series of steps, is the filter. The filter could be behind us. Maybe planets like Earth are rare. Maybe life almost never begins. Maybe complex cells are a biological miracle. Maybe multicellular organisms usually fail to emerge. Maybe intelligence capable of science is so unlikely that Earth is one of the only places where it ever happened. If the strongest filter is behind us, then humanity has already passed through the narrowest part of the path. That would make us extraordinarily fortunate. It would also make life on Earth more valuable than we normally understand. If intelligence is rare on a cosmic scale, then our planet may carry one of the few places where the universe has become able to study itself. But the filter could also be ahead of us. Maybe technological civilizations commonly appear, but rarely survive. They discover powerful energy sources, alter their climate, build dangerous weapons, create unstable technologies, exhaust critical resources, or lose the ability to cooperate before they become a long-lived interstellar society. This version changes the meaning of the silence. The empty sky would not be evidence that intelligence is rare. It would be evidence that intelligence has a short life expectancy. Civilizations may repeatedly reach the same dangerous stage and then disappear. The frightening part is that a civilization does not need to destroy every individual overnight. It only needs to lose the stability required for advanced technology. A global society could fragment, knowledge could be lost, infrastructure could fail, populations could shrink. A species might survive biologically while its detectable technological phase ends. From another star system, Earth would then briefly light up with radio leakage, satellites, and industrial activity, and later become quiet again. 100 years of radio technology feels important to us. To the galaxy, it is almost nothing. This is where the lifetime term in the Drake equation becomes crucial. Imagine that technological civilizations appear frequently, but remain detectable for only 200 years. The Milky Way could have hosted thousands of civilizations at different times without any two existing close enough at the same moment to communicate. The galaxy would not be permanently empty, it would be out of sync. One civilization rises, listens, hears nothing, and disappears. 10,000 years later, another does the same around a different star. Their signals pass each other in the darkness after both societies are gone. This is not the dramatic destruction shown in movies. It is a timing problem, a cosmic missed connection. The Great Filter also forces us to think about discoveries in a strange way. Suppose a future mission finds simple life beneath the ice of Europa. That would be one of the greatest scientific discoveries in human history. But in the logic of the Great Filter, it might carry an uncomfortable implication. If life begins independently in two places within one solar system, then the origin of life may not be the rare step. Suppose we later find complex multicellular fossils on Mars, or evidence that life arose on many nearby worlds. Each discovery would suggest that another early step is common. That would push the unknown filter farther down the path, possibly toward intelligence, technology, or survival. This does not mean discovering alien microbes would actually predict human extinction. The probabilities are too uncertain, and the assumptions are too simplified. But the idea reveals why the Fermi paradox is connected to our future. We are not only searching the sky for other civilizations. We are trying to understand whether civilization itself is a stable phase. Look at the powers humanity gained in a very short time. In a few centuries, we learned to reshape landscapes, alter the atmosphere, split the atom, and modify genes. Our wisdom did not grow at the same speed as our tools. We still make decisions using minds shaped for small groups, immediate threats, and short-term rewards. The danger may not be one particular technology. The danger may be the gap between what a civilization can do and what it can responsibly control. Nuclear war is one example. Environmental collapse is another. Engineered pathogens, uncontrolled autonomous systems, and other risks could also threaten a society. And some may become more dangerous precisely because civilizations are connected. A system can spread resources, but it can also spread failures. Still, the Great Filter should not be treated as a prediction. It is a framework. There is no scientific evidence that all civilizations destroy themselves. Humanity is the only test case we have, and our story is not finished. It is also possible that advanced civilizations become more stable over time. They may learn to manage planetary systems and distribute themselves across multiple worlds. Technology creates risks, but it can also create defenses. Telescopes can find asteroids. Medicine can stop diseases. Clean energy can reduce environmental pressure. Knowledge can be preserved. The same intelligence that creates a filter may also recognize it. Perhaps the transition from a short-lived civilization to a durable one is not impossible. Perhaps it is simply difficult. That distinction matters. An impossible barrier means the silence is our fate. A difficult barrier means the silence is a warning. And warnings can be useful. The silence may be a warning, not a verdict. But before we decide the universe is full of ruined civilizations, we should consider a much less dramatic explanation. Maybe no one is missing. Maybe we simply have not looked properly. When people hear that SETI has found no confirmed alien signal, it can sound as though humanity has searched the galaxy and come back empty-handed. We have not. Our listening has only just begun. The search for extraterrestrial intelligence is often compared with looking for a needle in a haystack, but even that image is too simple. A normal haystack has 3 dimensions. The SETI search space has many. We need to choose a location in the sky, a distance, a vast span of light years between us and them, a range of frequencies across the electromagnetic spectrum, a signal strength, a bandwidth, both hidden within the noise. A time, a repetition pattern, spanning eons of galactic history, a polarization, a transmission method, and a type of technology. A civilization may broadcast continuously or only once every 1,000 years. Its signal may be narrow and artificial-looking or spread across a wide band. It may use radio waves, optical lasers, infrared communication, neutrinos, physical probes, or methods we have not invented. It may aim a message directly at Earth or transmit in another direction. It may have stopped broadcasting before our species evolved. It may send a signal that passes Earth while our telescope is pointed somewhere else. This is not one search. It is an enormous collection of searches through a multi-dimensional space. Researchers have tried to estimate how much of that space humanity has examined. The answer is tiny. Our atmosphere contains industrial chemicals that would not exist at the same levels without technology. The night side glows with artificial light. Radar beams leave the planet. Satellites surround Earth. Large solar arrays, cities, mines, and transportation networks alter the surface. But here is the humbling part. Most of these signs would be extremely difficult to detect from interstellar distances. Our ordinary radio leakage weakens as it spreads. Many modern communications use lower power, narrow beams, fiber optic cables, and satellites rather than blasting strong signals into space. From far away, Earth may not look like a loud beacon. It may look like a barely detectable planet that became noisy for a short time and then learned to whisper. This creates another possible solution to the Fermi paradox. Advanced civilizations may become harder to detect as their technology improves. Our imagination often moves in the opposite direction. We picture older societies using more energy, building larger machines, and announcing themselves across the galaxy. But technological progress can also mean efficiency. A mature civilization may waste less energy. Its communication may be tightly directed. Its computers may be small. Its population may stabilize. Its activity may move underground, underwater, into virtual environments, or into compact habitats where little escapes. A society that can control its energy perfectly may produce fewer visible signatures than a young industrial planet. There is also the problem of assumptions. SETI often looks for signals that we know how to recognize as artificial. A narrow radio tone is interesting because natural cosmic sources usually do not produce extremely narrow, stable transmissions. But an alien technology is not required to resemble ours. A scientist living before radio could not have designed a radio search. A civilization thousands or millions of years beyond us may use physical processes we currently classify as background noise. We might already possess data containing a technosignature and lack the concept needed to recognize it. This is not a claim that every unexplained astronomical observation is alien. Unexplained means unexplained. History gives us many examples of strange signals that eventually received natural or human explanations. Pulsars were once jokingly labeled little green men because their radio pulses were so regular. They turned out to be rapidly rotating neutron stars. Fast radio bursts were mysterious for years. Many are now associated with extreme magnetic objects and energetic cosmic environments, although research continues. The famous WOW signal detected in 1977 remains interesting because it was strong and narrowband, but it was never repeated, and no confirmed extraterrestrial origin has been established. Scientific caution is not a refusal to consider aliens. It is the method that prevents us from calling every mystery a discovery. A true detection would need to survive repeated observation, independent confirmation, equipment checks, interference analysis, and every plausible natural explanation. The first convincing sign of alien technology may not look dramatic. It may begin as a strange line in a data set, a signal that repeats, a chemical imbalance that should not be stable, a pattern in starlight that refuses to disappear. Weeks or months may pass before scientists understand what they are seeing, and even then, the discovery may not be a message. It may be evidence that someone existed, a technological fossil crossing the galaxy long after its creators are gone. Space is not only large, it is separated by time. When we look into space, we look into the past. Light from the moon takes a little over 1 second to reach us. Sunlight takes about 8 minutes. Light from the nearest star system takes more than 4 years. Light from a star 1,000 light-years away began its journey when much of the modern world had not yet been built. This means there is no single present moment shared across the galaxy. Suppose a civilization 1,000 light-years away points a telescope at Earth today. It does not see our cities, satellites, aircraft, or radio towers. It sees Earth as it was around the year 1026. From that distance, modern humanity has not appeared yet. A civilization may have built a powerful transmitter 5,000 years ago and disappeared 4,000 years ago. Its signal could still be traveling toward us. Or it may have passed Earth during the age of the dinosaurs, when no one here could detect it. Two civilizations can exist in the same galaxy and never overlap in a meaningful way. Distance becomes delay. A conversation across 1,000 light-years requires at least 1,000 years for a message to arrive and another 1,000 for a reply. That is not a conversation in the human sense. It is correspondence between generations. The people who send the first message may know they will never hear the answer. The society that receives the reply may be completely different from the one that asked the question. This could discourage deliberate communication. Why spend enormous energy sending messages to a world that may not be inhabited when the message arrives? Why reveal your location to a civilization you cannot understand? Why build a transmitter for descendants who may not share your priorities? Human beings already struggle to maintain projects for decades. Interstellar communication may require institutions that remain focused for centuries or millennia. It is possible. It is just not simple. In the vast ocean of time, we have only just begun to search. Consider Earth's own detectable period. For billions of years, our planet carried life without producing technology. For hundreds of thousands of years, humans existed without radio. Strong artificial emissions have been present for little more than a century. If humanity remains detectable for 10,000 years, that would still represent a tiny fraction of Earth's lifetime. A distant observer would need to look at the right planet during the right 10,000-year window. Now multiply that timing problem across the galaxy. This may explain how life can be common while contact remains rare. The galaxy could contain many inhabited planets, but only a few technological societies at any one time. Some worlds may hold microbes. Some may support intelligent animals that never develop industry. Some may have ruins. Some may be millions of years away from their first radio transmission. The sky could be full of life at different stages, with almost none of it synchronized. There is another possibility. Perhaps intelligent civilizations do not remain on the surface of planets for long. They may transfer more of their activity into machines. They may live in artificial habitats, around cool stars, or in regions optimized for computation and energy efficiency. They may explore with robotic probes rather than biological bodies. A machine can survive acceleration, radiation, and long travel better than an organism. If advanced societies send self-repairing probes, those machines could outlive their creators. This returns us to Fermi's original problem. Where are the probes? Some researchers have proposed looking for artifacts in the solar system. No confirmed alien artifact has been found, but the solar system is vast, and our close inspection of it is limited. Again, absence of evidence is not automatically evidence of absence, but as searches improve, the silence becomes more informative. Every nearby star observed at high sensitivity rules out certain kinds of transmitters. Every planetary atmosphere studied rules out certain industrial signatures. Every survey that finds no giant artificial structures tells us that those structures are not common. If advanced technological societies are common in the Milky Way, most of them are not behaving in the loud, expansive, easily visible ways that older science fiction imagined. They may be quiet, they may be short-lived, they may be distant, they may be rare, or they may have reasons not to attract attention. They may be quiet, they may be short-lived, they may be distant, they may be rare, or they may have reasons not to attract attention. Silence is not the same as absence. A person hiding in a dark room is still there. A civilization may decide that broadcasting its location across the galaxy is unwise. There are peaceful reasons for staying quiet. Interstellar messages may be expensive. There may be little benefit in shouting toward stars that cannot answer for centuries. A society that values privacy may have no interest in expansion. Its attention may turn inward, to art, science, virtual worlds, or forms of experience we cannot imagine. It may communicate through narrow beams aimed only at known partners. From outside, that civilization would be almost invisible. There are also cautious reasons. When two human cultures with very different technologies have met, the weaker society has often suffered, even when destruction was not the original goal. An advanced civilization could conclude that contact creates unpredictable risks for both sides. It may follow a policy of observation without interference. This idea is sometimes called the zoo hypothesis. In that scenario, Earth is not ignored because it is empty. It is ignored because we are being allowed to develop without contact. The obvious problem is coordination. For the zoo hypothesis to explain the entire sky, many civilizations would need to follow the same rule, or one powerful group would need to enforce it. No evidence shows that this is happening. It remains speculation. A darker version suggests that broadcasting is dangerous because hostile civilizations may exist. That idea will receive its own full investigation in a future episode. For now, the important point is simple. Intelligent beings may not treat communication as harmless. Humanity itself has debated whether we should actively send powerful messages toward nearby stars. Listening is passive. In the silence, we wait for a sign. Broadcasting announces that a technological civilization exists here. Some scientists argue that Earth has already been detectable through atmospheric changes, radar, and radio leakage, so deliberate messages add little risk. Others argue that we do not know enough to make decisions on behalf of future generations. The debate reveals our own uncertainty. We often assume aliens would be curious because we are curious. We assume they would explore because we explore. We assume they would communicate because we want communication. But intelligence does not guarantee shared motives. Another civilization may not think in individual minds. It may be distributed across machines, ecosystems, or networks. It may experience time differently. It may not recognize radio as meaningful. It may not separate technology from biology. The word civilization may be too human. We are searching for another version of ourselves, because ourselves are the only example we understand. This is unavoidable, but it creates blind spots. A dolphin is intelligent, yet it does not build cities. An octopus solves problems with a nervous system unlike ours. Ant colonies coordinate complex behavior without a central planner. Trees exchange chemical signals through roots and fungi. Earth already contains many forms of intelligence, communication, and organization. Only one produced radio astronomy. Alien life may be even less familiar. It could live beneath kilometers of ice with no view of the stars. It could evolve in a dense atmosphere where fire is impossible and metallurgy never begins. It could inhabit an ocean world with no easy access to electricity. It could become intelligent, but remain trapped by its planet's gravity. A species on a super-Earth may require far more energy to reach orbit. A species around an active red dwarf may survive underground and never develop visible surface industry. A planet can produce intelligence without producing a space program. This may be one of the quietest solutions to the Fermi paradox. The galaxy could contain minds that never become astronomers. They may look up through an ocean, an ice shell, a cloud layer, or not look up at all. And even among species that reach the stars, we may be assuming that we arrived at an ordinary time. What if we did not? The universe is about 13.8 billion years old. That sounds ancient, and it is. But some stars will continue shining for trillions of years. Small red dwarf stars burn their fuel so slowly that the future lifetime of the universe may be far longer than the time already passed. This creates a surprising possibility. Humanity may not be late. We may be early. The first generations of stars contained almost no heavy elements. Elements such as carbon, oxygen, silicon, and iron were produced inside stars and spread through space when stars died. Rocky planets required earlier stars to live, manufacture those elements, and release them. Life could not begin immediately after the Big Bang. The universe had to become chemically mature. Our sun formed relatively late in the Milky Way's history, about 4.5 billion years ago. But that does not mean most life should already be older than us. Suitable environments may become more common over time. Long-lived stars may provide stable energy for periods far beyond the current age of the universe. If life around red dwarfs is possible, and that remains an open question, then most living worlds may exist in the distant future rather than the present. We could be among the early technological civilizations simply because the universe has barely started its long habitable era. This explanation does not require humanity to be unique. It only requires us to be near the front of the line. There are problems with the idea. The Milky Way still contains many stars older than the Sun. Some likely formed rocky planets billions of years before Earth existed. Even if the universe is young compared with its future, there has already been enough time for earlier civilizations to appear. So being early may reduce the paradox without completely removing it. Another related idea is that complex life requires a narrow period of galactic conditions. The early galaxy had more radiation, more massive stars, and more violent events. Later, heavy elements became more available, but planetary systems may also face changing risks. Perhaps there is a broad galactic habitable zone in both space and time, a period when enough heavy elements exist, but catastrophic events are not too frequent. If Earth formed near the beginning of that favorable era, then advanced life elsewhere may only now be starting to emerge. This would make the silence less like an abandoned city and more like a neighborhood before sunrise. The houses are there. The lights simply have not turned on yet. There is no way to confirm this from one planet, but it changes the emotional meaning of the Fermi paradox. The silence may not mean everyone died. It may mean almost no one has had time to arrive. Perhaps the first civilizations are separated by such large distances that each believes it is alone. Perhaps one of them is listening around a star on the other side of the Milky Way tonight. Their radio telescope points into darkness. Their scientists study thousands of planets. Their children ask whether anyone else is out there. And their sky gives them the same answer ours gives us. Nothing clear, nothing confirmed, only possibility. So where is everybody? After more than 70 years of discussion, the honest answer is that we do not know. The Fermi paradox has no single accepted solution. Life may be rare. Complex life may be rare. Technological intelligence may be rare. Civilizations may be brief. Interstellar travel may be too costly. Signals may be difficult to recognize. Societies may become quiet as they advance. They may exist at different times. They may avoid contact. Or we may simply be searching an ocean with a glass and calling it empty. Several explanations can also be true at once. Life may be common, intelligence uncommon, and long-lived civilization rarer still. Technological societies may appear occasionally. They may survive for a few thousand years, send only narrow signals, and remain separated by distances too large for conversation. That kind of galaxy would contain others without ever feeling crowded. The most important lesson is not that aliens must exist. It is that the evidence is still incomplete. We have confirmed thousands of worlds, but examined only a tiny fraction in meaningful detail. We have listened to portions of the radio spectrum for short periods. We have only recently gained the ability to study the atmospheres of small planets around other stars. Our search is not old. It has barely begun. There is also a deeper reason the question matters. Every proposed answer reflects something about humanity. When we imagine civilizations destroying themselves, we are thinking about our own risks. When we imagine them hiding, we are thinking about fear. When we imagine them exploring, we are thinking about curiosity. When we imagine them choosing silence, we are thinking about maturity or isolation. The evidence is still incomplete. We have confirmed thousands of worlds, but examined only a tiny fraction in meaningful detail. Our search is not old. It has barely begun. Every proposed answer reflects something about humanity. When we imagine them exploring, we are thinking about curiosity. When we imagine them choosing silence, we are thinking about maturity or isolation. The silence is not a wall, it is an invitation. It invites us to consider how rare and fragile our own civilization might be. It invites us to value the intelligence we already have and to protect the only living world we know. In the coming decades, our eyes and ears will become more sensitive. We will search for the chemicals of life in the air of distant worlds. We will scan more stars for more kinds of signals. Whether we find a neighbor or continue to find only ourselves, the search changes us. It forces us to think on a scale larger than our own lives. The great silence remains the greatest mystery of the modern age. But remember, the silence of the galaxy at noon does not mean the neighborhood is empty. It may only mean that we are the first to wake up, and the day is still young. Keep looking up, keep listening, because the answer is out there, waiting for us to find it. Space is not just distance, it is time, and our journey has only just begun. The sky becomes a mirror. But it is not only a mirror, it is a real place containing real worlds, and some of those worlds may have histories as complex as ours. A planet does not need to hold a civilization today to matter. A dry riverbed on Mars could preserve evidence that life once existed. An ocean beneath Europa's ice could contain biology that began independently. A distant atmosphere could show a chemical pattern produced by living organisms. A narrow signal could appear in a telescope and repeat. Any one of these discoveries would change the human story. Until then, silence should not be confused with emptiness. Silence is a result. It tells us that loud, obvious nearby civilizations have not revealed themselves in the places and ways we have searched. It does not tell us why. Perhaps we are alone. Perhaps we are first. Perhaps others are too far away. Perhaps the galaxy is filled with quiet life. Or perhaps at this moment, another species is looking toward our sun and asking the same question. Where is everybody? We may not receive an answer in our lifetime, but the search itself matters because it forces us to decide what kind of civilization we want to become. One that burns brightly and disappears? One that turns inward and stops looking? Or one that survives long enough to hear a distant reply? For now, Earth remains a small world orbiting an ordinary star, surrounded by a galaxy that has kept its secrets. The night above us is dark, the instruments are listening, and somewhere inside that silence may be the answer. Whether intelligence is a common feature of the universe or one of its rarest events. This is the unknown sky, where we investigate the questions waiting beyond the edge of what humanity knows. Next week, we ask what happens when matter, light, and time fall into a black hole. Until then, keep looking up.